Um, right. So we're going to look at complexity classes and reductions today. And I went through the slides some of you shared with me, the slides made by your faculty, and that is a very theoretical way of approaching the subject, which is formally right. But I wanted to approach it in a slightly different way. So some of the topics you will see in those slides are more towards theory of computation than DAA. And those topics have been put there just to give you some context about the whole idea of complexity classes and reduction. So Turing machine and all of that, which you would have seen there, is not strictly related to complexity classes, but it is in one sense the foundation. So I am choosing to give you a different sort of context, a different sort of foundation. So because most of us here are engineers or aspiring engineers, so people who are going to be solving problems in future, hopefully. So I'm going to give you a slightly different foundation, a different context, which is more suited to that perspective. uh, Ultimata, whatever you're supposed to know about complexity classes and reductions, that you will know. But the intro part, the Turing machine and all those TOC parts, I'm choosing to skip that. If any of you is interested in learning that, you can always reach out to me later. But for the exam point of view, main and that will be covered. The intro will be slightly different. So with that, let's get started. I'm going to start with a very basic question. And let's keep this interactive, especially the initial part. So why do we learn DAA? Any of you can unmute and answer it. It's open to all of you. Anyone wants to just take a guess?
It's not enough to like just solve the problem, but make sure that the solution is efficient as well. So that's where designing an algorithm properly comes into picture.
Right, that's very correct. So the whole idea is to solve problems in a more efficient way rather than just using brute force, right? So how do we do this? As she said, we use different algorithm design paradigms. You look at the problem and you sort of think in the problem, okay, if we use this design paradigm, the solution is likely to be easier to arrive at, and that's how we proceed. But is that always enough? If yes, you can justify. If not, then give me a scenario where you think just looking at different design paradigms is not enough. Anyone? Okay, I'll give you a few directions to think of. What if no design paradigm seems to work? What if you look at a question and you think of the 3, 4 design paradigms you've learned and none of it seems to be suitable for that particular question? That could be one scenario. What if you use a design paradigm and you come up with an algorithm, but it is computationally too expensive? It's going to take a lot of computation to come up with the solution to the extent that it's impractical. That might be the case. What if your problem is not solvable at all? And first of all, how do you look at the problem and realize this problem is not solvable versus I am not able to think of the solution to this problem? So how do you decide that? That is one question. And so in such cases, will it help to play around with the problem itself instead of trying to play around with the solution? Because everything we've done so far, divide and conquer, dynamic programming, greedy, backtracking, branch and bound, whatever, is tinkering with the solution, trying to come up with a solution using different heuristics, different methods. Instead of doing that, in all these cases, will it help to look at the problem itself? That is what we're going to primarily be dealing with in complexity classes and reductions, right? So the basic idea is sometimes solving a problem becomes easier when you either slightly tweak the problem or you solve a different but related problem. So this part, we will be coming back to this at least twice in the course of this session. So I'll give you a simple example. Uh, let's say you guys are going to have a CIA for DA. So your faculty tells you, it's the same syllabus. They're giving you two options. Either it's going to be a subjective kind of a test where they give you the question and you have to write the answer, or it's going to be MCQ. What would you choose? I'm pretty sure most of you would, or many of you would choose MCQ, right? So it's the same syllabus, it's the same questions which are going to be asked, but when you tweak the question from a subjective to an MCQ, somewhere most people's confidence level goes up because the answer is also given in the question paper. So along with a few other options. So they feel like I'll be able to handle this better or this is easier to handle, right? So it's the same question which you are being asked, but by slightly tweaking the format, it becomes easier to solve. And another, the second case, solving a different related problem. So let's say you have the MCQ test. You come to the second question, you look at the question, you look at the options, you're not sure, you're not able to answer it. So you skip that question, you move on to question 3, 4, 5. Then you come to the sixth question. It's a different question, but it's something related, something probably an extension of the concept which was tested in question 2. And when you solve the sixth question, you realize, oh, okay, so this is what the solution to question 2 should have been. So you go back to question 2 and now you're able to answer it. So that thing happens with all of us, right? So sometimes it becomes easier to solve a problem either when you slightly tweak the problem itself or when you solve a different but related problem, a problem whose solution you can use to get back the solution of the first problem. So can we exploit these two properties and use that to help us in these situations? This is what the basic idea of complexity classes and reductions is. This is why we are going to be studying these topics. So any questions so far?
No.
Okay, moving on. So before we begin, yeah, so how can we compare the complexity of problems? So I'm not talking about the efficiency of solutions. I'm talking about the complexity of problems themselves. How can I say this problem is easier or this problem is tougher than problem Y? So what's the method to judge? Can someone give me any answers? Guys, feel free to like tell whatever comes to your mind. This is no judgment. You don't have to worry about your answer having to be right. Okay, I'll give you something to think about. Do you think uh, comparing the algorithms or comparing the solutions is a good way to say this problem is easier than this problem?
Maybe not.
Why not?
Because like each algorithm uses a different method as a whole to find the answer, and like it's not same quantities can be compared, but maybe different methods comparing them isn't the best way.
Exactly. So the just because the time complexity of one algorithm is less than the other, it does not mean this problem is easier. It depends on the algorithm. It depends on a bunch of things. So the classic example for this is the sorting problem. You have multiple. You have bubble sort, merge sort, insertion sort, blah blah blah. So one of these is permutation sort. So quick reminder of permutation sort: you take every possible permutation of your sequence and you check which of them is sorted. So if you have n elements, then there are n factorial ways of ordering them, I believe, which means you have n factorial permutations. For every one of them, you are going to check if it is sorted. So roughly the time complexity is order of n factorial. And for your traveling salesman problem, if I remember correctly, the brute force algorithm is something to the order of 2 power n. Generally, n factorial is going to be greater than or equal to 2 power n for all input sizes greater than 4. Does that mean sorting problem is harder than TSP? Obviously not, right? So it's not right to compare algorithms and say problem X is easier or harder than problem Y. So we need some other more sensible metric to compare the easiness or hardness of problems, which brings us to this notion called lower bound of a computational problem, which means Irrespective of what algorithm I'm using, this problem cannot be solved in better time than this. So if I take this problem itself, I need at least this much time complexity to solve it. Even if I'm using the most efficient algorithm, the best hardware, irrespective of all that, at least this much time is required. For example, you take the sorting problem again. Even the most efficient algorithm must visit all n numbers at least once. You cannot sort n numbers without at least looking at each number once. The reordering and all of that, it might take n square iterations, it might take n log n iterations, it might be done in n iterations, depending on how intelligently you do the swaps. But the bare minimum necessity is every one of those n elements must be visited at least once. So the lower bound is going to be at least order of n. Now, mathematically, you can prove that for any comparison based sorting, the actual lower bound is order of n log n. But if it is, we're saying the lower bound is n log n, means any algorithm I use is going to be at least n log n. Then obviously it is going to be at least n, right? So this is a good enough lower bound for our purposes right now. I'm not going to, like, my intention here is not to derive the formal lower bound of the sorting problem. What I'm trying to drive home is the idea that there is a notion of time complexity, upper bound, lower bound for algorithms, and there's a completely different notion of lower bound for a problem, which is irrespective of what algorithm I'm using, this problem requires at least this much time, right? So is the idea of lower bound clear? I assume that's a yes. Now we move on. So with that in mind, look at this question. If the lower bound of problem x is less than the lower bound of problem y, can we say x is easier than y? Again, this is an open question. So let's say you have two problems. One problem, the computational lower bound is, let's say, order of n. For another problem, the lower bound is n squared. So is that enough to conclude that the first problem is easier than the second? Say something, guys.
Not really sure about this.
Okay, so yeah, so well, the answer is, as she said, not really, right? Because uh, it depends on the algorithm. So this problem requires at least O of n, but that does not mean it can be solved within O of n itself, right? O of n is for O of n or n log n or whatever is just a conservative lower bound. I'm saying I will definitely need at least this much, but I'm not saying within that much I can give you a solution, right? So if you take a sorting problem, uh, O of n being the lower bound makes sense because yes, every one of those n numbers must be visited at least once. But if you're going to use any comparison based sorting, you cannot do better than n log n, and this is mathematically proven. So just because my theoretical lower bound is n doesn't mean I can solve a sorting problem in O of n. With, of course, there is an algorithm to solve in O of n, but I'm not going into that part right now. What I'm trying to say is the lower bound of the problem does not become necessarily the lower bound of the best algorithm. Such an algorithm might not yet have been developed. So lower bound of a problem is a theoretical notion. So just because lower bound of x is less than lower bound of y, you cannot say x is easier than y. Make sense?
Yes.
Okay. So conversely, if the lower bound of y is greater than the lower bound of x, can we say y is at least as hard as x? I'm not saying y is tougher than x, but can we say y is at least as hard as x? So the answer is kind of yes. So when I say kind of, what I mean is we will be looking at a more formal definition of at least as hard when we come to reductions and stuff. But in one sense, yes. So if problem X, at least theoretically, can be solved with just O of n time. But problem y, even theoretically, it requires O of n squared. So in one sense, at least on paper, at least theoretically, y is going to definitely take more time than x. So in that sense, we can say y is at least as hard as x. This is just a rule of thumb way of judging complexities. This is, we'll be looking at a more formal technique later, but for starters, judging the complexity of problems based on their lower bounds is a reasonable way to compare, provided you're making the right kind of inferences. So this thing which we saw is not a sensible inference to make. This thing, to some extent, yes. Make sense? Yes, no? Right. Okay. I assume that's a yes. Now I have a quick task for all of you before we move to the next topic. So I want to see who answers this question first. And you have exactly 10 seconds from the time I display the question. Is everyone ready? Yes. Can
Yes.
I have, okay. Yes. Exactly 10 seconds. Whoever gets this right, you can just feel free to unmute and give me the answer. You can use your phone, Google, whatever. The time starts now. Time up. Any answers?
Is it 37 and 12,907?
37, yes, and the other was something close. I'm not sure. I wrote it down. Yeah, is this the number you mentioned?
Yeah.
Yes, right. Great job. You got it. You used what? What
No,
did
I
you
didn't
use?
get it. I used Claude.
Ah, okay. I mean, expected. Right. So now look at the question in green. So I tell you it is this. Am I right? So now, how will you check this? You will multiply these two numbers and you will check if the product is this big number here, right? So
Yeah.
now the actual question I wanted to ask is, which of these problems would take you less time to solve, provided you did not have Claude or AI support or Google? You have a calculator on hand. Which of the
Probably checking that, but like verifying the answer
right,
would be
exactly.
better.
So if I give you an answer, verifying whether it's correct or wrong is going to be easier. Finding an answer on its own is going to be difficult, right? So this kind of relates to, okay, I'll come to that later. Yeah, so this kind of relates to this thing I said here, right? So if they give you a subjective question and you have to write the answer, that's one thing. If it's an MCQ and you have one right answer and three wrong answers, it is just identifying the right one. So although the question is the same, the answer is the same. When you change the format of the question, it becomes in some cases easier to solve, right? So that's the idea. Most problems have a decision version and an optimization version. When I say optimization version, I'm using it in a very broad sense. I do not necessarily mean maximize or minimize something. And I just mean find the best possible solution. In some cases, it could just be find a solution. So for this question here, it's just find a solution, right? So when I say optimization version, I simply mean you have to find the solution, solve the problem and find the solution. And when I say decision version, it is something like I give you a solution and I ask you to check, is this a valid solution? Is this the best possible solution? So a decision version is basically anything which outputs either a yes or a no. And in most cases, the decision version is easier to solve than the optimization version, right? For obvious reasons. It's always easier to check something. Okay, almost always easier to check something than to actually solve and arrive at the answer, right? So the whole idea of complexity classes, if you remember that we started out, was we want to solve problems better, but not in terms of designing algorithms, but by playing around with the questions. One way to do that is, if you have an optimization version, if you can convert it to decision version, it might make it easier for you to solve, right? That's the idea. So you get the idea? Any questions so
Yes.
far? Okay, I assume there are no questions. So we'll look at a few examples of decision version and optimization version. Starting with the classic sorting problem. Optimization version is sort the sequence x1, x2 up to xn. Again, as I said, this is just about finding a solution or finding the solution. It is not necessarily maximize, minimize. Optimization is used in a very broad sense here. So optimization version is you sort the sequence and you give the sorted output. Decision version is you give it a sequence and you ask, is this sorted? So this will tell you, yes, it is sorted or no. So it's easier to check whether a sequence is sorted, right? You can do it in one traversal, O of n. Whereas this one, it will take if you the most effective comparison based sort I can think of is merge sort, and there it will take me n log n. So the decision version is easier here. Next thing, vertex cover. So vertex cover is, I'm sure all of you know it by now, but just to recap, you have a graph, you have vertices and edges. You have to select some subset of vertices such that every edge in the graph has at least one endpoint in the subject, in this subset, right? So for vertex cover, the optimization version would be, let's say, find a vertex cover or find the minimal vertex cover, find the smallest number of vertices you have to take so that it forms a vertex cover. Decision version is there a vertex cover of size something, right? So given a size or given, let's say, a subset of vertices, it becomes easier to check whether is this a vertex cover. Okay, again, let me make another point. Is this VC? So there can be multiple decision versions and multiple optimization versions also. Okay, right. Let me write this. Find VC of size k, right? So it all depends on how you frame it, and that again depends on what you want to solve, what you want to find out. So your optimization version could be find a vertex cover of size k, or it could be find the smallest possible vertex cover. Decision version could be either you ask, is there a vertex cover of size k, or you give it some subset of nodes and you ask, is this a valid vertex cover, right? So in both cases, you will see that this is in some way or the other easier to solve than this, right? Any questions so far? No. Okay, moving on. Quick homework / example. 0-1 knapsack. Try it out. Someone tell me what the decision version and optimization version will be. Any answers? You don't have to like state the entire problem formally mathematically. Just give me a rough description of what you think the optimization version should be and what you think the decision version would be.
Optimization might be finding the weights, like find how you can put the weights to get the max profit, the
Right,
given
yeah.
limit.
So find the objects you will select or the objects you
Yeah,
will put in the knapsack basically, such that this is the maximum weight and this is the and you maximize the profit, right?
yeah.
Maximum weight is equal to, let's say, some W, and profit is maximized. Very good. And the decision version is?
I mean, given this weight, is it the maximum profit or like something with a yes or no?
Yeah, given a configuration or given a set of chosen items, uh, is this the best profit you can get? Something like that. Right? Great. So that's the idea. So the key takeaway here is, in most cases, the decision version will be easier to solve than the optimization version. Not necessarily all cases. Okay, so with that, so any questions so far? None? Okay. So we'll move on to reductions. Formally, we will be defining reductions a little later in this session. Right now, it's just an informal glimpse. So again, we come back to this same thing we started with. So we saw an example, or we were discussing this first point so far, right? So you tweak the problem by changing the optimization version to the decision version. In one way, that is going to help you make the problem easier. The other thing you can do is solve a different problem, a related problem, and use that solution to get this. So this also I gave you an example. You don't know the answer to the second question on an MCQ test. You go ahead, you solve the sixth question. That gives you an idea or reminds you of something. That helps you go back and solve the second question, right? So the sixth question was a different question, but something related. And the idea was you were able to use the solution of question 6 to somehow arrive at the solution of question 2. So that is what the whole idea of reductions is. So we look at reductions formally soon, but the basic idea is this. You cannot solve problem Y, but you can solve problem X, and you can use the solution of X to somehow solve Y. You do so. That is what reduction is about, right? So, okay, before I go to complexity classes, any questions so far?
No.
Right. So with that basic intuition, we will now formally step into complexity classes. So complexity classes is basically you divide your problems, computational problems into different categories based on their complexity, how easy or how hard they are to solve. The first category is P, which stands for polynomial time, which means these problems are solvable in polynomial time. So let's take a look at these terms. Solvable means it's the optimization version. So it means you are able to find a solution or find the best solution depending on how your optimization version is framed. You're able to find a solution or find the best solution in polynomial time. Polynomial is your n square, n cube, n power 1000, all of that is polynomial. N factorial, 2 power n, all of these are not polynomial, right? So anything that is exponential is not polynomial. You know what a polynomial is, so I don't need to spend too much time on it. So polynomial time is any problem whose optimization version you can find in polynomial whose optimization version you can solve in polynomial time, right? So is class P clear? Yes, no?
Yes.
Right. Can someone give me an example of a problem belonging to class P, a computational problem? Any simple,
Bubble
sorry?
sort?
A problem, not an algorithm. You're close, but what's the problem there?
Sorting problem.
Sorting problem, right? Sorting problem. You can do it in n log n, you can do it in n square. Any of it is polynomial, right? So example for this would be sorting problem. Another example you could say is find max, find min. All of that you can do in O of n. Sum of elements. Matrix multiplication, you can do it in, if you have two n cross n matrices, I think O of n cube, you have the brute force algorithm. So that all of that is solvable in polynomial time. So these are examples, right? We move on to the next class, which is NP, non-deterministic polynomial. So, okay, two things here. Firstly, NP is not non-polynomial. It is non-deterministic polynomial. This is something a lot of people get confused about. So please remember the expansion, right? Secondly, what is deterministic? I will talk about it tomorrow when I teach approximate algorithms and randomized algorithms. If I forget, someone please remind me tomorrow. So I'll tell you what deterministic is when we talk about that. It's more relevant there. So as of now, NP stands for non-deterministic polynomial. And the idea is this refers to the class of problems which are verifiable in polynomial time. We're not talking or making any comment about the solvability of these problems. They could be solvable in polynomial, they could be solvable in exponential, they could be not solvable at all, as in no algorithm has been developed so far to solve these problems. Could be anything, but they are verifiable in polynomial time. So if I give you a solution, you can verify whether it is correct or not in polynomial time, meaning the decision version can be handled in polynomial time. This is a non-deterministic. This is what we mean when we say a problem belongs to NP class. So NP makes sense?
Yes.
Can someone give me an example? Any example, guys? The problem can be solvable in polynomial, exponential, unsolvable, anything. It should be verifiable in polynomial time. That's all.
Traveling salesman.
Okay, how would you verify? Okay, what is your decision version first?
Sorry.
What is your decision version? How do you frame your decision version question?
Actually, I didn't like exactly complete studying traveling salesman. So
No, that's fine. You know how TSP is, you know the TSP problem definition?
yeah,
Huh, tell me the problem definition. Like roughly, it doesn't have to be mathematical, just whatever you know about TSP.
yeah. So it has to like cover all the.
You have a
I
bunch of
think what.
cities connected like
Hmm.
this, and there are some weights, right?
Yeah.
And you have to find a path which covers all these cities, right?
Yeah. All the
Right.
yeah edges.
All the edges, yes. So all the edges or all the vertices? You have to visit all cities, right? Isn't that how TSP is
Okay.
defined?
Yeah. Vertices.
Guys, can someone correct me, because I've also not looked at it in a long time. You have
I
to visit
think
all
all
cities.
cities have to be visited
Which means
without
all
repetition, I guess. Yeah.
all nodes, all vertices have to be touched, right? So that is the problem. So your optimization version would be find some path which does this with minimum cost or maximum cost, whatever. So how are we going to phrase the decision version? There are multiple ways of phrasing it. So how do you want to put it? You can either put it like, is there a path which touches all vertices exactly once in X cost? That is one way. The other way is you give it a path and you're like, is this a valid solution? Does this touch all cities without repetition? Right? That is also a decision version. So if you put it the second option which I told you, like, does this touch all cities? If you phrase it, yes, it is verifiable in polynomial time. You just have to take the path which is given, start from the first vertex, go till the last. Just follow the path. If you have V vertices, it's going to be O of V, which is polynomial. If you put the decision version in like the first way I said, like, is this the minimum cost wala path? Then you have to again check all paths before you can decide that this is the minimum cost. So that is not verifiable in polynomial time. That will take, I think, 2 power n. Right? You get what I'm saying?
So like verifying whether the path is like less than a given, like let's say k is you're saying that is like 2 power n complexity.
Verifying, no. Okay, what I mean is this a valid solution verifiable in polynomial time? Does this touch all paths, and is it less than k? That is less than k cost. That is verifiable in polynomial time. But is this the best solution? Is there no path less expensive than this? that you cannot verify in polynomial time.
Yeah, okay, thank you.
Right? Makes sense, everyone? So yeah, that's a good example in the sense that for the same problem, depending upon how you phrase the decision version, it can either be NP or some other class, right? It can either be verifiable or non-verifiable in polynomial time. So TSP, if you put it like, is this a valid tour which visits all cities? Yes, that is verifiable in polynomial time. If you phrase the decision version some other way, it might not be verifiable, right? So, okay, that's one example. Any other examples of NP? Can someone give me? Okay, I'll give you an example. Prime factorization of a number. You have to split a number into prime factors. So, if I give you, so the decision version is basically where I give you a sequence of prime factors and I ask you, is this the prime factorization of the number in question? You simply have to multiply everything. If your answer is equal to the number, then your decision version outputs a yes. Otherwise, it outputs a no. So it is verifiable in polynomial time. Solvability, we are not making any constraint at all in NP, right? So how would you find the prime factorization of a number? You could probably take all the prime numbers from 2 till the given number, try every possible combination. It could be n factorial, or you come up with a better algorithm which finishes it in O of n square, whatever. We're not bothered about the time complexity of solving. This problem is verifiable in polynomial time, so it goes under NP. Make sense? Everyone?
Yes.
Any questions so far? Okay. So now, before we move to the next class of problems, yeah, verifying is easier than solving almost always. This is what we've been talking about for a long time now, right? The decision version is in most cases somewhat simpler to accomplish than the optimization version. Example is this thing we saw. To find a pair of numbers without using a computer would have been a pretty difficult job for you. But when the two numbers were given, it was simply a question of multiplication and comparison, right? So anything that is, so basically the point is solving is harder than verifying. Maybe I should put it that way. That would make it more sense. So solving is harder than verifying. Again, almost always, not necessarily always. So anything that is solvable in polynomial time is definitely verifiable in polynomial time. If you can find the solution itself in, let's say, n square, you're not going to take n factorial to verify the solution, right? So anything that is solvable in polynomial is also verifiable in polynomial. So P is a subset of NP. P is basically anything solvable in polynomial, right? And NP is anything that is verifiable in polynomial. So P is a subset of NP. That makes sense?
Yeah.
Everyone? Are we on the same page so far?
Yeah.
Right, great. So, moving on. Next thing we go to is NP hard. So, PNP mudichachu. Now we come to NP hard. A problem is said to be NP hard if all problems in NP are polynomial time reducible to this problem. So, again, reducible formal definition I have not given you yet. But if you remember what we saw previously, it is you don't know how to solve your given problem, but you solve another problem and you are able to use that solution to get back this solution, right? So இங்க என்ன சொல்றாங்கன்னா all problems in NP are reducible to this problem. So let's say I'm calling this problem X, a problem X. All problems in NP are polynomial time reducible to X, which means if I solve problem X, then using the solution of X, I can solve all problems in NP within polynomial time. Then I say X is NP hard. I'll repeat, you have a problem X and you have a bunch of problems in NP. NP again is verifiable in polynomial time, right? So if I solve X alone somehow, using the solution of X, all the problems in NP, I can somehow or the other solve them in polynomial time. Then this problem X is said to be NP hard, right? So the idea here is all NP problems are at least as hard as X, right? So you have to first get the solution of X and then you do some operation, some manipulation in polynomial time to get a solution to these NP problems, right? Which means all of these are at least as hard as X. So because you have to solve X first and then you have to do some manipulation, which may be easy, may be hard, may be straightforward, may involve a lot of thinking and a lot of work. But to start with, you have to solve X. Ilana, you will not be able to solve these other NP problems, which means all NP problems are at least as hard as a particular problem X. Then we say X is NP hard. So is everyone clear with the idea of NP hard? Any questions? Any of you wants me to repeat this?
Could you repeat it like once?
Yeah, sure. So a problem X is said to be NP hard if all problems in NP are polynomial time reducible to this problem X. Okay, so I'll give you the example my faculty gave me when he was teaching this. So let's say there is a multi-story building. You want to reach the 12th floor. Now, from the 10th floor to the 12th floor, you know how to go. Like, you know how to, maybe there is some, let's say some special kind of elevator or something there, and you know how to operate that. But you don't know how to go from the ground floor to the 10th floor, right? So if you want to reach the 12th floor, you have to first reach 10th floor. From there, you know how to take yourself to the 12th floor, right? So you have two problems here. Problem X is how do I reach 10th floor? Problem Y is how do I reach 12th floor? Now, if I somehow solve X, if someone does some magic or if I learn how to fly and I reach 10th floor, from there, within polynomial time, I'll use the elevator and I'll go to 12th floor. So going to 12th floor is at least as hard as going to 10th floor. I have to go to 10th floor plus some additional work, which I know how to do. So to solve problem Y, I have to solve problem X. I need to get someone to carry me to the 10th floor, or I need to find a way to climb some pipe or something. Somehow I have to reach 10th floor and then some manipulation of the elevator will take me to 12th floor. So that's the idea. So you have a problem X. You somehow manage to solve that problem X. Using that solution, you do some manipulation and you're able to solve all other problems which are in NP. Then X is said to belong to NP hard. So if you look at this elevator example, getting to 10th floor was the tough part, right? That is the thing we didn't know how to do. Once you got there, going to 12th floor was cakewalk. You know how to do that. It took you some time, but you know how to reach there. You reached there. So getting to 10th floor was the question mark. You had to figure some way out of doing it. So that's the whole idea. You have NP and you have NP hard. If you are able to solve NP hard, you will be able to solve everything in NP. That's the idea. NP hard is literally harder than NP, at least as hard. That's the idea. So I have a problem X. If I solve X using that solution, I can solve all NP problems in polynomial time. That's what NP hard is. Yes, someone was going to say something. Any questions?
What do you mean when you say all problems in NP? Like, is it one NP problem or is it every NP problem?
The entire set NP.
Oh, Okay.
So the entire set of problems, okay, so how that happens is, so if you know the solution to this problem X, we'll use some reductions again, formally we're going to see, to somehow reduce your NP problems to something done with X. So for example, going back to our the multi-story building, if I know how to reach 10th floor, from there I have an elevator. So I can go to the 11th floor, I can go to the 12th floor, I can go to the 20th floor, I can go to the terrace. Any problem that is about reaching a floor higher than 10, I can solve it. It is not just 12th floor, correct? So yeah, so that's the idea. If you know how to go to 10th floor, you can go to any floor higher than that. Similarly, if you know how to solve this problem X, you can solve anything in NP simply by doing some particular manipulation. So in our building example, the manipulation would be you press the correct floor number on the elevator, that kind of thing.
In this example, getting to the 10th floor is the NP hard problem, right?
Correct, correct. Any other questions? Anyone? Do all of you follow what I'm saying? Is anyone lost? Anything you want me to repeat? I know it's not very intuitive to understand NP hard. It takes a few, you have to go through the material twice or thrice. But the basic idea is, once you solve an NP hard problem, all the NP and P problems become easy to solve. That's the idea, basically. Right, shall we move on? I assume that's a yes. So yeah, NP hard, by the way, are the hardest problems known till date. Some of them we have not even come up with solutions yet, right? So with that, I'll move to NP complete. NP complete very simply is NP intersection NP hard, meaning firstly it is an NP hard problem, meaning if you solve this problem, everything in NP can be solved. And secondly, it is NP, meaning it is verifiable in polynomial type. So what this means is, for NP complete, basically, we don't have a method of solving it in polynomial time yet. But if we can solve this, then everything in NP will become solvable. Secondly, as I said, we don't have a method of solving yet, but we can verify it in polynomial time. So it is quite literally the intersection of NP and NP hard, which we call NP complete. So, okay, I didn't give you an example for this one, right? So, an example for this one could be your TSP optimization version. And for this one also, okay, let me not give you the same example. So, your vertex cover, your independent set, your 0-1 knapsack, all the optimization versions of these are NP complete. And we'll be looking at a proof shortly. Right, so I'll quickly show you the diagram. So as of now, ignore this part. Let's focus only on the left hand side. So this circle represents NP, which is verifiable in polynomial time. A subset of that is P, which is solvable in polynomial time. As I said, if it is solvable in polynomial, it is obviously verifiable in polynomial. So P is a subset of NP. Next, we have NP hard. It means different colors. NP hard is the hardest problems known. So if this pink problems are solved, all the blue and green can be solved. So if the definition was confusing you, maybe you can remember using the diagram. So if any problem in the pink zone can be solved, then using that, all the problems in the blue and green zones can be solved. It's quite literally like saying, this is the toughest exam. If I can cross this exam and do this well, then I can do any exam in the world or any exam in my course well. It's that kind of stuff. And NP complete is the intersection of your pink and blue, meaning it is the person. Oh my God. It is one of the hardest problems. So if you solve that, all the NP problems can be solved. And also this one is verifiable in polynomial time, right? So that is NP complete. So this part, it's just if your P and NP were equal, meaning if anything that is verifiable in polynomial time was also solvable in polynomial time, then this entire circle becomes one entity. That's all. This is not really important, so you don't have to pay too much attention to it. So, oh my God, it's not okay. Right. Right. So, is this diagram clear so far? Are you guys okay with these concepts to some extent?
So the NP complete aren't solved yet, right?
Yeah, most of them are not solved. Right.
I have a doubt.
Yeah.
I'm not sure if this would confuse people further, but like the things that so NP hard like basically let's say there's a problem X, and then if
Hmm.
that can be solved, then all the problems in NP can be solved. Is that's the
Correct.
essence?
Correct. Hmm.
Like, is it like in polynomial time? Is that what you mean, or time is
No, no.
totally not
So,
related?
as in, okay, I'll go back to the building example. I get to the 10th floor. From there, I can go to any of the higher floors in polynomial time. From 10 to any of the higher floors, I can go in polynomial time. But to go to the 10th floor, I can take exponential also. There is no bound on that.
Yeah. Okay. Thank you.
Again, that's a point I will be making when we come to reductions. But yeah, so to solve x, you don't have any bound, like it has to be polynomial, not necessarily. It can be exponential, it can be anything. Once x is solved, using that to solve any of the NP problems is only going to take you polynomial time. Right? Right. So now, so typically this kind of diagrams are called Venn diagrams, right? But here it's called an Euler diagram. The reason being, in a Venn diagram, your circles are usually circles. They are like closed polygons. Here, one of the curves is open, indicating a set which is not completely closed, right? The NP-hard set is open. That is why we call this an Euler diagram and not a Venn diagram. Now, can someone tell me why it's open? Why is it not a closed circle? Any guesses? Anything, anything.
Maybe because there's not a defined set of problems that you can keep like
Right,
coming up
exactly.
to.
So new problems will keep getting discovered every day. So you don't have a universal set saying these are the only problems that exist in the universe. So you cannot say this is you cannot close this set. New things will keep coming up every day. That's the reason this set is open, and that's why it's an Euler diagram and not a Venn diagram. So yeah, okay. Are we comfortable with complexity classes? Can we move to reductions?
Yeah.
Okay. Do you guys want a break or shall we continue? I'll tell you what's left, what I've planned. So yeah, the definition of reduction, a few examples. There's just one property called transitivity and one something about how to prove NP completeness. And we'll be seeing examples for these things. Examples I've planned 5 examples. I think 2 of them are pretty trivial. The other 3 I will like take some time to explain. So do you guys want a break or shall I proceed now? Tell me something, guys.
Anything works.
Okay, I will proceed for now, but if you feel like you want a break anytime, let me know. Okay? Right. Sorry, we'll see. Oh my God, did I click something? Where it is? Right. So we'll see what reductions are, right? Formula, we're going to define reductions. Now, again, the idea is you solve a related problem and use that solution to solve your original problem. Something we've been talking about from the start of the session. So, that is what I mean when I say I reduce problem X to problem Y or vice versa. So I'm I don't know how to solve question number 2 on my MCQ test. I solved question 6. I used that solution to solve question 2. Meaning, I'm reducing question 2 to question 6. So if 6 is done, then I know how to solve 2. So the difficulty of 2 gets reduced to the difficulty of solving 6. Or the difficulty of reaching 12th floor gets reduced to the difficulty of reaching 10th floor. Because once that is done, I know how to move forward from there. That's the idea of reductions, right? Problem y is said to be reducible in polynomial time to problem x if, knowing the solution of x, y can be solved in polynomial time. Again, there is no restriction on x. To answer the question Nedra asked a while ago, x need not be solvable in polynomial time. You can take 10 years to reach the 10th floor. But once I reach the 10th floor, I only need a few minutes to reach 12th floor. That's the idea. So you can take any amount of time, any algorithm, any magic you can use to solve x. But once I know the solution of x, I can use that solution to solve y in polynomial time. That's what I call as y is polynomial time reducible to x, and less than equal to p is how we mathematically denote it. So is the definition of reductions clear? Everyone? Yes?
Can you explain with the building example?
Okay. So, okay. Well, my original problem was I wanted to go to the 12th floor, right? But if I am on the 10th floor, I know how to go to the 12th floor. So my the problem that remains to be solved is reaching the 10th floor somehow. So I have to figure out how to reach the 10th floor somehow. That is a difficult problem. I don't know what to do. I have to find someone to ask, or I have to figure something out. But once I reach the 10th floor, I simply need to press a button on an elevator and I will go to the 12th floor, right? So knowing the solution of x, knowing how to get to 10th floor, y can be solved in polynomial time. So knowing how to get to 10th floor, I can reach 12th floor in polynomial time from 10th floor. So it might take me 10 years to figure out how to reach 10th floor. But once I reach 10th floor somehow, it's only going to take me, let's say, 20 seconds to board the elevator, press the button and reach 12th floor. So this part is going to be polynomial, provided you know this, right? Now this might or might not be known to you. That is the problem. So if this thing, if reaching 10th floor is going to be an NP hard problem, you might not know a solution at all. There might be no way to climb. There might be no one who can carry you. You will not have wings. So reaching a 10th floor might seem impossible as of now. With your existing resources, with the existing research, reaching 10th floor is impossible. But if hypothetically I reach 10th floor, it is going to take me polynomial time to reach 12th floor. That is what I mean when I say the 12th floor problem is polynomial time reducible to the 10th floor problem. Make sense?
Yes, yes. Thank you.
Any other questions, anyone? We'll be looking at examples, but like the definition makes sense. Okay, we have a few examples. Shall I start with I think I'll start with the trivial ones. Okay, so we'll start with a very simple example. So you're going to show how 01 knapsack is reducible to subset sum problem. So can someone define the 01 knapsack problem roughly? Come on, guys, you're supposed to know this by now.
You choose like there are certain items with certain weight, and then there's a profit that's comes with the item. So you choose in such a way that your profit is maximum.
Yeah, profit is maximized and
And
you
it's
have
within the,
you have an upper bound on your bag capacity, right? Your bag can only hold so many kilograms or whatever. Right. So keeping all that aside, essentially, it's a kind of choosing a set of elements, keeping the capacity aside for now. Okay. Or yeah, you can. Okay. You keep the profit part of it aside for now. It's the problem is choosing a set of elements such that the sum of their weights, weight 1, weight 2, let's say you're choosing some k elements, this is going to be equal to c, less than equal to c, right? Where if c is your capacity. Does this make sense? Yes or no?
so we're just using the weights for now.
Choosing elements such
Okay.
that the weights add up to c or as close to c as possible.
Yeah.
Right. There is another constraint, added constraint of profit, of course. But yeah, for now, let's assume we just want to fill the bag. So now, how is this related to subset sum? Subset sum, okay, I'm sorry. Are you guys aware of the subset sum problem? Anyone? I don't think you would have come across it in your syllabus, but anyone who came across while preparing for something? Okay, so you have basically a set of elements x1, x2 up to xn. You have to choose a subset such that sum of the elements of the subset is equal to some given number n. So that is the subset sum problem. So for example, let's say the set given to you is 1, 2, 3, 4 and n is 5. What could be the solutions? Quick.
2,
If it,
3,
2, 3,
1 and 4.
1, 4. Yeah. And 3, 2, 4, 1 also. Same thing. Order is immaterial, right? So this is the subset sum problem. Now, how can we relate this with this? So you understand the problem definitions, right? I'll tell you how the reduction actually happens, but both the problem definitions are clear. Everyone? Yes, no, say something, guys.
Yeah.
Okay, so I'm going to solve the decision version of the knapsack problem. I am phrasing the decision version like this. Is there a knapsack with some configuration or some choice of items such that the weight equal to C and profit equal to K? Of course, strictly speaking, it would be less than equal to, but for the sake of simplicity, I'm choosing to define my decision version like this. Remember that for the same problem, you can define your decision version in different ways. I want to give you a simple example for reduction, so I'm choosing this method. So profit, some value of K I'm choosing, weights, some value of C. Now I'm asking you, is there a knapsack like this? So how can I reduce this to subset sum? It's very simple. So you have weight 1, profit 1, weight 2, profit 2, let's say weight and profit n, right? So from this, I am going to choose some weight A, profit A, weight B, profit B, so on up to weight X, profit X. I'm going to choose some subset such that the weights is going to be, the sum of the weights is going to be C and the sum of the profits is going to be K. So so this is one subset sum, this is one subset sum. If both of these are going to give me a yes, then the answer to this is going to be a yes. Otherwise, it's going to be no. Correct? You guys understand what I'm saying? Yes, no, say something, guys.
Yes.
Right. So essentially, what's happening is, see, someone's giving me the 0 1 knapsack problem. The decision version, this decision version, basically, someone's asking me to solve. I don't know how to solve it, but I have a machine which can solve the subset sum problem for me. Again, the decision version of the subset sum. It will, if I give it a subset and if I give it the target, it will tell me whether the sum is equal to the target or not. So using that machine, how can I solve 0 1 knapsack? It's very simple. I will give it the subset WA, WB, blah, 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 and I'll give it the target C. I will get back either a yes or a no. Similarly, I'll next give it the subset PA, PB, blah, 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 and I'll give it the target K. Again, I'll get back a yes or a no. Now, once I have these two, once the subset sum has been solved, I simply have to compare both of these. I have to do an AND operation basically. If both are a yes, my output is a yes. Even if one is a no, my output to this problem is a no, right? So this machine, which solves the subset sum, I don't know how much time it is taking. I don't know what algorithm it is using. I don't know what is its time complexity. I don't know what magic is happening inside. And frankly, I don't care. Once I get the solution from that, I only need to do an AND operation to get the solution for this. So once this problem is solved, this one becomes solvable in polynomial time. AND operation is O of 1, which is polynomial. So I can say this is reducible in polynomial time to subset sum. Make sense? Yes or no?
Yes.
Anyone has any questions on this? Want me to repeat something?
Akka, could you repeat the last part around
Okay, you understand how you can solve knapsack using subset sum, correct?
yeah.
Right. So what I'm saying is, sorry, I need to solve knapsack. It's the pen. I need to solve the decision version of 0 1 knapsack. I don't know how to solve it. I have a machine that can solve the decision version of subset sum. I give it a subset, I give it a target. It will give me either a yes or a no. So what I'll do is, I will take my subset weight A, weight B, so on up to weight X, X or K, whatever, and the target C. I will pass these here. I'll get either a yes or a no. Again, I'll use the machine. I'll take the profit A, profit B, the corresponding profits, and this target, I think I called it K. I'll pass that also to the machine. Again, I'll get a yes or a no. So now this is solving my problem X. My problem X is subset sum. This machine is solving it somehow, and it is giving me two answers, answer 1, answer 2. I don't know how much time this took. I don't know what algorithm was used, and I don't care about any of that. Now, once I get these two, I have to check if this is also a yes and this is also a yes. Then there is a knapsack with weight equals C and profit K. So I will return a yes. In any other case, I will return a no. So what I'm doing here is a simple checking or an if-else condition, which is going to take me polynomial time. So once subset sum is solved, I can solve 0 1 knapsack in polynomial time, which means 0 1 knapsack is reducible in polynomial to subset sum. Clear?
Yeah.
So the idea, I will quote the words my faculty used when he was teaching this topic to me. If there is a black box which can solve your problem X somehow, then using the solution for X, you can find the solution for Y in polynomial time. The black box is our machine, which is somehow doing subset sum. We don't care about how much time it takes or what algorithm it uses. We trust that the answer it gives is right. Now, using that answer, I simply have to run an if-else condition and I get my answer for the problem I wanted. So, my problem is reducible in polynomial time to this subset sum problem. Make sense?
Yeah.
Any other questions? Okay. Control D. Right. Let's look at one more example. Try not to take too much time.
Akka,
Yes. Someone called me.
Akka, you said subset sum is at least as hard as knapsack.
Hmm.
Isn't knapsack at least as hard as subset sum?
Yeah, you can prove the other way also. Both are reducible to each other. Both are in both are in NP complete. So this is reducible to that, and that is reducible to this.
Okay.
So maybe you guys can try that out. Try to reduce subset sum to knapsack. It should be easier intuitively. Right. So to solve one knapsack, we had to use two subset sums. To solve one subset sum, I think one knapsack should be sufficient. So that's a homework question. Maybe you guys can try it out. Try to reduce subset sum to knapsack. Meaning, you have a black box that will solve 0-1 knapsack ka decision version. How will you use that to solve the decision version of subset sum? That's the question. Try solving it whenever you find time. Okay, we'll do one more example. Vertex cover and independent set. Now, has this been taught to you in class? I'll not ask you to solve it, don't worry. Just was it like discussed? Was this reduction example taught? This is one of the most.
I have this doubt.
Hmm.
In the previous example, they are
Hmm.
both only the decision version of those problems, right?
Yes.
Not the
yes.
optimization
No,
versions.
no, decision version.
Okay. Thank you.
So, yeah, that again reduction. You will choose how to frame your what version you want to reduce. Generally, we work with decision versions only, and even in the decision version, you can choose how to frame your decision version. So, like I said, I put weight equal to C. If you want to make it a little harder, you can make it weight less than equal to C. Profit greater than K. So all that is your choice. Whatever assumptions you're making, you have to state them clearly and they should be logical. That's all.
Got it.
Okay. So yeah, can someone define the vertex cover problem quickly?
So in a graph, we choose vertices such we choose the minimal number of vertices such that all the edges are covered.
Correct. For every edge in the graph, at least one of the endpoints is chosen, right? So okay, so we are again going to be dealing with decision versions only. Given a graph G is equal to V comma E. V is the set of vertices and E is the set of edges, usual terminology. And let's say, what do I call it? Let's say small v is a subset of V. Is small v a vertex cover? This is the question, right? And independence, this is the decision version. And by vertex cover, what I mean is exactly what she said. So it's a subset of vertices such that at least one endpoint of every edge in the original graph is present in that subset. I hope all of you know what vertex cover means. Does anyone want me to draw and show an example? I assume that's a no. I assume all of you are familiar. Okay, similarly, some decision version here is given G is equal to V comma E, and let's say I is a subset of V, is I an independent set. And by independent set, what do we mean? Again, a subset of vertices such that there is no edge. What's the definition of independent set again? Can someone help me out?
No two edges share a same vertex.
Okay, it's a wait.
It's the complex of vertex cover, opposite of vertex cover.
Dependent set is a subset of vertices where no two vertices are connected by an edge. Again, it's a subset of vertices. Okay. Yeah. I'll write this down. At least one endpoint of every edge must be in the subset, right? No two nodes or vertices in the subset must be connected by an edge, right? So these are the two definitions. Problem definitions are clear, everyone? Anyone wants me to repeat? Okay, I assume everyone's fine. So now we'll see how to reduce one to the other. We'll be seeing both ways. Okay, that's the slide. I will, and okay, wait 1 second. Just 1 second. Oh my God, it's not working. Should I copy paste to a copy paste is not working. Okay, I wanted to like screenshot the proof and put it here, but it's not there, so I will try to write it down. Okay, right. So first of all, let's the entire set of vertices in the graph is capital V, right? So now let's say I have S is a subset of V. S is an independent set. So somehow I have been able to find an independent, did I spell it right? Independent, yeah. I have been able to find an independent set. Using this, I want to find the vertex cover. How we can do this is, so you take any two edges u comma v, any two vertices u comma v from your original graph, right? So now both of these cannot be in S at the same time, right? I'm sorry, and B belong to S, not possible. Okay, I'll repeat this. So you have V, which is your set of vertices in the graph. You have S, which is a subset of vertices, and we are told that S is an independent set, meaning no two vertices in S are connected by an edge. Right. Now you take any pair of vertices in V which are connected by an edge, right? So it is not possible that both of them are present in S, correct? Because I'm saying U and V are connected by an edge in my original graph. Then U can belong to S or V can belong to S, but not both. Because if both belong to S, then S would not be an independent set. The whole idea of an independent set is no two edges in it are connected. These two are connected. So these both cannot belong in S at the same time. So at least one of U comma V belongs to V minus S. Are you all following me so far? This is the set difference. Are we good so far? Yes, no? Something, guys. Are you all awake?
Akka, could you like
Repeat?
repeat it once?
Okay. Do you guys understand what is a vertex cover and what is an independent set? Or do you want me to
Yeah.
repeat that? You understand the definitions.
Yeah.
Okay. So in this part alone. So okay, I will delete this and write again. Take the pencil. Polish. Okay. You have V, which is the set of all the vertices in your graph. Good. You have S, subset of V, meaning sum of the vertices subset you have taken. Now, given S is an independent set. Independent, I spelled it right, set, which means no two vertices in S are joined by an edge. Are we correct so far? Yes, no?
Yeah.
Yeah. Now, continue here. Yes. Put this here. Now, pencil. Take any two nodes u comma v from the graph, right? So these are vertices. So what are the possible cases? U belongs to S, V does not belong to S. U belongs to S, V belongs to S. U does not belong to S, V belongs to S. U does not belong to S, V does not belong to S. These are the four possible conditions, right? You take two nodes, either each of them belongs to this subset S or they do not belong. These are the only four possible configurations. Am I correct?
Yeah.
Right. Now, one thing I'm saying is U, V, edge exists. There is an edge from U to V in the graph. This is, I've kept this in mind while selecting the edges, selecting the nodes. Now, is this possible? If is it possible for both of them, both U and V, to belong in S? Given there is an edge and given we have this condition,
No.
right? Does everyone understand why it's not possible? The condition says if both of them belong to S, they should not be joined by an edge. And my choice of UV is such that they are joined. So both cannot belong. So this is not possible. So we have only these three cases to deal with. Move them up. Okay. So we'll start with, oh, sorry, this has to be, B does not belong, my bad. Okay, so these are the three cases we have now. The other case where both belong was ruled out, right? Are we good so far?
Yeah.
So now there is, so if V does not belong to S, what does that mean? V belongs to the entire set minus S. Am I right?
V belongs to entire.
And the whole superset vertices minus S, set difference.
Yeah.
You
Yeah.
have an entire set of vertices V. If this is S, this is going to be V minus S, right? So a node either belongs here or it belongs here. Or if this UV is confusing you, take it as XY, no problem. If this V and
Yeah.
that V are confused.
Makes
Right?
sense.
So similarly here it means U belongs to V minus S. And here it means both U and V belong to V minus S. So whenever you have an edge from U to V, at least one of the vertices belongs to the set V minus S. Do we see that? Whenever there is an edge between U and V, at least one of the two vertices belongs to V minus S. Does everyone agree? These are the only three cases possible, and in each of those cases, at least one of the concerned vertices belongs to V set difference S. Correct?
Yeah.
So V set difference S is a vertex cover. Do you get it? For every edge, at least one of the endpoints or at least one of the corresponding vertices belongs to this set. So is a vertex cover. So if I have a black box that can solve independent set problem and give me set S, S being an independent set, I simply need to do set difference V minus S to solve vertex cover problem. So vertex cover is polynomial time reducible to independent set. Make sense?
So like we get a vertex cover, I mean not vertex, sorry, independent set S. So like if we do like remove the S from V, like
Set
the
difference. What you
set
get is the
difference,
vertex cover.
vertex. Okay, okay.
Yes, exactly.
How so?
Any-
Like, is there a? I'm not able to visualize how, like, if you subtract
This is
what it
the
becomes.
proofs. So yeah, so you take S is your independent set. It's a subset of your vertices. S is the independent set. So whenever you consider any two nodes from the graph, it is not possible that any two nodes such that they are connected by an edge. Okay, wow. So for every edge, or let me put it the other way around. For any edge in your original graph, both the nodes cannot belong to set S because it is an independent set. The whole idea of independent set is both the endpoints of an edge cannot belong there. So at least one should be in V minus S. Correct?
Yeah, that part I got.
So essentially for every edge, at least one endpoint is going to be in V minus S. And that is the whole definition of vertex cover, a set where for every edge, at least one endpoint should be in this set. That is what we mean by vertex cover.
Oh, okay, like that.
So V
Yeah,
minus S is a vertex cover if S is an independent set. Is that part clear?
Yep.
Okay. So now we'll try to do the page. Okay, I will not take up too much time. Okay, you know what? I'll leave the opposite as a homework to you. You try it out. If you're not sure, we can uh, discuss this tomorrow. Prove that independent set is polynomial time reducible to vertex cover. It's just the other way around. So basically what I want you to prove is if I tell you V minus S is a vertex cover, show that S is an independent set. This is what I want you to try proving. Pretty simple, similar logic. Try it out. Yeah, that is there. What is pending? Okay. Yeah, I'll just do these two concepts quickly. No big examples for this. And then tomorrow we'll do one gadget-based reduction and the approximation randomization algorithms. Okay, so this is just some theory. I'll quickly take this and I'll wind up. So first thing I'll do is transitivity of reduction. So there's nothing very complicated here. So if x is reducible in polynomial time to y and y is reducible in polynomial time to z, then obviously x is reducible to z. Transitive property, meaning if you know the solution of y, you can solve x in polynomial time. If you know the solution of z, you can solve y in polynomial time, which means you know the solution of z, you can solve x in polynomial time. So is the property clear?
Yes.
So where this is useful is, let's say someone's asking you to prove vertex cover is reducible to clique or something like this. Now you don't know how to directly prove this, but you know how to prove independent set is reducible to clique, and you know that VC is, you know how to prove this is reducible to independent set. Now you can do this proof separately, and say by transitivity property, vertex cover is reducible to clique. Abdin, you can say. So in that place, this will be useful. Clear? Okay, one last topic. For this one, I'll probably give you a simple homework. It's very straightforward. So, how to prove that a problem is NP complete? So, who remembers the definition of NP complete, which we looked at some time ago?
It is
No
the
one?
intersection of NP and NP hard.
Very good. NP intersection NP hard, right? So, if you want to prove that it is NP complete, we have to prove these two things. So, to prove that it is NP, you just have to show that it is verifiable in polynomial time. That will usually be like common sense. If I tell you, what do I say? Someone give me an example of a problem. In a 0-1 knapsack is NP complete prove na. Decision version can be solved in polynomial time. It is common sense to prove it. I give you a number of elements, weights and profits. You just have to sum up and check if weight less than equal to capacity, and that's all there is. Decision version. So summing up is obviously polynomial time. So it is proven that this problem is verifiable in polynomial time. Done. How do we prove that it, right? So that is how you prove that it belongs to NP. How do we prove that it belongs to NP hard? Now the definition of NP hard is everything in NP should be reducible to this problem X, right? Right?
Yes.
So how do we set about doing that? We don't even know what is everything in NP. So how can we do that? So what we do is we take something from NP complete, and if you can prove that is reducible to X, what happens is, see, this is your NP complete, right? The pink part. So if NP complete is NP as well as NP hard. NP complete is a part of NP hard, which means all NP is reducible to your NP complete problem. And your NP complete problem, if you can prove that it is reducible to X, then by transitivity, all of NP is reducible to your X, which means X belongs to NP hard. So, sorry, this part will have been proven. So the intersection is NP complete. Does it make sense? Do you want me to repeat?
Could you please repeat that?
First point clear?
Yes.
This one, verifiable. Okay. Second point, see what I want to do is prove that X belongs to NP hard. If I prove that, what happens is NP intersection NP hard, I can show that X is NP complete. Okay, so to prove that X is NP hard, I have to say all of NP is reducible to X, which is impossible. I don't even know what all of NP is. But let's say I have a problem Y, which I know is NP complete. Now, NP complete is again NP intersection NP hard, correct? Yes or no?
Yes.
Which means Y belongs to NP hard, right? Which means all of NP is reducible to Y, correct? Yes or no, guys? Say something.
Yep.
Right. Now, if I can prove Y is reducible to X, some NP complete problem is reducible to my problem, then from this and this, by transitivity, all of NP is reducible to my problem, which means X belongs to NP hard, which is exactly what I wanted to prove. Right?
Yeah, but you have to show that Y is reducible in polynomial
So
time.
you will be given some problem Y, or you can take something which you know is NP complete, and then you have to think of a way to reduce something like this. So for example, you know that vertex cover is NP complete. Now you take vertex cover, you take your problem X and you try to prove that vertex cover is reducible to your problem X. So how you reduce is just thinking. You have to come up with the logic. That's the idea. I gave you one example today. No, two examples I think. We did that knapsack subset sum and we did vertex cover independent set, right? I'll do one or two more examples tomorrow, examples of trivial reductions, one gadget based reduction. There are a few more examples in the document. It's there in the drive folder, you can find it, or I'll share the link again. So if you try those questions out, you will get an idea of how to do reductions. I'll also give you like a few tips and some the other, but like how to approach reduction questions, we'll discuss in detail tomorrow. I just wanted to introduce the concept of reductions today, which I've done. So yeah, we'll discuss reductions in a little more detail tomorrow, and we'll do approximation randomization. So yeah, that's all I wanted to teach today. If if there are any questions, I'll take it now. Any questions?
Akka, can you explain the knapsack is as hard as subset sum problem is as hard as knapsack? Only the polynomial verifying part.
The one we did or the other way around?
This one only.
Okay. I'll take another page. Okay, so in knapsack, I have a set of selected weights, weight A, weight B, up to weight X, and a selected set of profits of the corresponding items, okay, up to profit X. And I want to check if the total weight is equal to C and the total profit is equal to some K. Yes or no? This is what I want to check. Clear so far?
What did
I
you say?
don't. Sorry? You said something?
No, Akka, continue.
Okay. Subset sum. What I have a machine that will solve the subset sum problem for me. When I say it will solve, what I mean is I'll give it an input which is a subset of or a set of elements x1, x2 up to xn and a target. If I give these two inputs, it will do something and it will return a yes if sum of all the elements is equal to target. Otherwise, it will return a no. What exactly it does inside is a black box, which I don't care about. This is what the machine does. Clear so far?
Yes, Akka.
Okay, so I'm going to use this machine 2 times to solve my knapsack problem. First time, I'm going to give it weight A, weight B up to weight X, and target is equal to C. And it's going to return me an answer 1. Let's say I call it answer 1. Second time, I'm going to use the same machine. I'll give it profit A, profit B up to Px. Sorry, set bracket. Target is equal to K. Again, it returns an answer 2. So this machine solved the subset sum problem for me, the decision version of the subset sum problem for me, right? Now,
Yes, Akka.
what this answer is going to be a yes or a no. This answer is going to be a yes or a no. Now, if both of these are a yes, then the answer to my knapsack problem is going to be yes. Otherwise, the answer is going to be no, right? Isn't that what my knapsack problem asked for?
Yes,
Right?
Akka.
So I just have to take these. I have to do an if condition. If A1 equal to yes and A2 equal to yes, return yes, else return no. This is an if else condition which is going to take over 1 time. So if someone solves the subset sum problem for me, I can use that solution to solve 0, 1 knapsack in polynomial time. So 0, 1 knapsack is polynomial time reducible to subset sum. All I'm doing is I'm performing subset sum with the weights ones, with the profits ones. That's all. Make sense?
Akka, in zero and knapsack problem, it is not necessary that we reach the capacity, right? We are within the capacity is the constraint, but in this case, we are considering that it should be equal to that capacity.
Yeah, I just took a very simple, again, it depends on how you frame the decision version. I have framed it as total weight equal to capacity just because I wanted to take a simple case. If you want to make it total weight less than C, you can make it like that. How you use the subset sum machine will change in that case. You will have to run it multiple times for values C, C minus 1, C minus 2, so on and so forth, whatever. How you use the solution of the subset sum to get the solution of knapsack will change depending on how you have defined the knapsack problem. But the core thing is, if you have a machine that will solve subset sum, you can use it to solve knapsack in polynomial type. That's the idea.
Okay,
The
Akka.
how is what reduction is all about. That depends on one, how your decision versions are framed, two, what your machine is taking as input and giving out as output, and three, your thinking.
Yes, Akka.
Any other questions from today's concepts? I will stop the recording now.